Have you ever wondered what lies beyond the event horizon? What mysteries are concealed within the depths of a black hole? Prepare yourself for a journey through space and time, where reality bends, and the laws of physics as we know them cease to exist. In this thrilling episode, we will dive into the heart of a black hole, explore its enigmatic properties, and discover the fate that awaits anything that dares to cross its boundary. Stay with us as we unravel the secrets of one of the most fascinating and terrifying phenomena in the universe. What would happen if you fell into a black hole? The answer may surprise you. The universe has many secrets, and black holes are among the most intriguing. Join us as we embark on a cosmic adventure to uncover the truth about these mysterious entities and what they hold for those who venture too close. Let's start by understanding what a black hole is. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. This collapse compresses the star's mass into an incredibly small and dense point called a singularity, where gravity is so strong that not even light can escape. Surrounding the singularity is the event horizon, the point of no return. Once anything crosses this threshold, it is inevitably drawn into the singularity. To truly grasp what happens when you fall into a black hole, let's imagine an intrepid astronaut bravely venturing toward a stellar mass black hole. As our astronaut approaches the event horizon, several remarkable and terrifying effects come into play. Firstly, let's talk about time. One of the most mind-bending aspects of black holes is their impact on time. According to Einstein's theory of general relativity, time slows down as you get closer to a massive object. For our astronaut, this means that as they near the event horizon, time starts to slow dramatically compared to someone watching from a safe distance. This effect is known as time dilation. Imagine our astronaut equipped with a clock and a friend watching from afar with another clock. As the astronaut gets closer to the event horizon, their clock ticks more and more slowly from the perspective of the distant observer. Eventually, right at the event horizon, time for the astronaut appears to stop entirely. This means that from the outside, it looks as though the astronaut is frozen in time at the edge of the black hole, never actually crossing it. However, from the astronaut's perspective, time continues to flow normally. Next, we must consider the effect of gravity, which becomes overwhelmingly powerful near a black hole. This immense gravitational force creates a phenomenon known as spaghettification. As our astronaut falls toward the event horizon feet first, the gravitational pull on their feet is significantly stronger than on their head. This difference in force stretches and elongates the astronaut's body into a thin, noodle-like shape. Though it may sound like science fiction, spaghettification is a very real and lethal consequence of black hole gravity. As our astronaut crosses the event horizon, several things happen simultaneously. The point of no return is passed, and the astronaut's fate is sealed. To an outside observer, they appear to freeze and fade away, their image becoming redder due to gravitational redshift, where light waves are stretched to longer, redder wavelengths by the intense gravity. Inside the event horizon, reality continues to warp. Space and time themselves are twisted beyond recognition. Our astronaut, now spaghettified, is on an inexorable journey toward the singularity. The laws of physics as we know them break down at the singularity. All known theories, including Einstein's general relativity and quantum mechanics, fail to describe the conditions accurately. It is a place where infinite density and zero volume coexist, a paradox that has puzzled scientists for decades. What lies within the singularity remains one of the greatest mysteries in astrophysics. Some theories suggest it could be a gateway to another universe or a different part of our own. Others propose that information about everything that has fallen into the black hole might be stored on the event horizon, in a concept known as the holographic principle. This principle posits that all the information contained in a three-dimensional region can be represented on its two-dimensional boundary, much like a hologram. Now, let's address a common question. Can anything escape a black hole? The answer lies in Hawking radiation, proposed by the renowned physicist Stephen Hawking. According to this theory, black holes are not entirely black. Instead, they emit tiny amounts of thermal radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, causes black holes to slowly lose mass and energy over time, eventually evaporating entirely. However, this process is incredibly slow for most black holes and would take longer than the current age of the universe for large black holes to evaporate. The study of black holes continues to evolve. With advancements in technology, such as the Event Horizon Telescope, we have captured the first ever image of a black hole, located in the center of the M87 galaxy. This groundbreaking achievement has provided us with invaluable data, bringing us one step closer to understanding these cosmic enigmas. In addition to stellar mass black holes, there are also supermassive black holes residing at the centers of galaxies, including our own Milky Way. These behemoths, millions to billions of times more massive than the Sun, play a crucial role in galaxy formation and evolution. The supermassive black hole at the center of the Milky Way, known as Sagittarius asterisk, is an object of intense study and fascination. Imagine, for a moment, the immense gravitational forces at play within Sagittarius asterisk. This supermassive black hole has a mass equivalent to approximately 4 million suns. If our astronaut were to approach this giant, the effects would be similar yet vastly amplified compared to a smaller black hole. The gravitational pull is so powerful that it influences the orbits of stars and other celestial bodies within our galaxy. Now, let's delve deeper into the concept of spaghettification and why it occurs. The process is rooted in the intense tidal forces near the event horizon. In simple terms, tidal forces arise from the difference in gravitational pull experienced by different parts of an object. For our astronaut, the gravitational force acting on their feet is much stronger than the force acting on their head. This difference creates a stretching effect, pulling the astronaut's body into a long, thin shape. Interestingly, the effects of spaghettification are not uniform across all black holes. In smaller black holes, the event horizon is closer to the singularity, resulting in stronger tidal forces. In contrast, supermassive black holes have a much larger event horizon, and the tidal forces are less extreme at this boundary. This means that if our astronaut were to fall into a supermassive black hole, they might cross the event horizon relatively intact, only experiencing the spaghettification effect much closer to the singularity. Another fascinating aspect of black holes is their role in the universe. Black holes are not merely destructive forces, they also contribute to the creation of new stars and galaxies. When a black hole consumes matter, it releases a significant amount of energy in the form of radiation. This radiation can trigger the formation of new stars by compressing surrounding gas clouds. Furthermore, the immense gravitational pull of supermassive black holes helps to anchor galaxies, maintaining their structure and stability. Let's explore the life cycle of a black hole. Black holes can form in several ways, the most common being the collapse of a massive star. However, black holes can also form through the collision and merging of smaller black holes or neutron stars. When two black holes merge, they emit powerful gravitational waves, ripples in spacetime that can be detected by instruments like LIGO Laser Interferometer Gravitational Wave Observatory. Over time, black holes can grow by accreting matter from their surroundings. This process occurs in accretion disks, swirling disks of gas and dust that spiral into the black hole. As matter in the accretion disk falls toward the event horizon, it heats up and emits intense radiation, often observed as X-rays. This process is not only a key mechanism for black hole growth but also a significant source of radiation in the universe. As black holes grow, they can eventually become supermassive. These colossal entities are thought to reside at the centers of most, if not all, galaxies. Their formation and growth are still areas of active research, with scientists exploring various theories, including the direct collapse of massive gas clouds in the early universe and the merging of smaller black holes over time. One of the most intriguing questions about black holes is what happens to the information about the objects that fall into them. According to classical physics, once something crosses the event horizon, it is lost forever. However, this idea conflicts with the principles of quantum mechanics, which suggest that information cannot be destroyed. This paradox, known as the information loss paradox, has led to various theories and debates among physicists. One proposed solution is the holographic principle, which suggests that all the information about the objects that fall into a black hole is encoded on the event horizon. This idea aligns with the concept of holography, where a three-dimensional image is encoded on a two-dimensional surface. If this theory is correct, it could mean that the information about everything that has ever fallen into a black hole is preserved on its surface, potentially allowing for its eventual retrieval. Another exciting development in black hole research is the study of wormholes. Wormholes are theoretical passages through spacetime that could potentially connect distant regions of the universe. Some scientists speculate that black holes might be connected to white holes, hypothetical counterparts that expel matter and energy instead of consuming it. If true, This could mean that falling into a black hole might lead to emerging in a different part of the universe, or even in a different universe altogether. However, these ideas remain speculative, as there is currently no experimental evidence to support the existence of wormholes or white holes. As we continue to explore the universe, the study of black holes not only deepens our understanding of gravity and quantum mechanics, but also challenges our perceptions of reality itself. They serve as natural laboratories, testing the limits of our knowledge and pushing the boundaries of human imagination. The mysteries of black holes inspire us to look beyond our current understanding and strive for new discoveries. In conclusion, falling into a black hole is an experience that defies our conventional understanding of physics and the universe. From the warping of time and space to the extreme gravitational forces, it is a journey into the unknown. While our brave astronauts' fate is sealed within the singularity, their story sparks curiosity and wonder, driving us to explore and learn more about the cosmos. As we continue to push the boundaries of our knowledge, who knows what new discoveries await us in the depths of space? The study of black holes is a testament to the human spirit of exploration and the endless quest for understanding the universe. Thank you for joining us on this incredible journey into the heart of a black hole. If you found this video as fascinating as we did, make sure to hit the like button, subscribe to our channel, and share your thoughts in the comments below. Your support helps us bring you more exciting content about the wonders of the universe. Until next time, keep looking up at the stars and stay curious.